You know the dream of traveling through time? It's as old as stories themselves. We've all thought about it, right? Seeing the future, maybe changing the past. But what if it's more than just a dream? Today, we're going to dig into what modern physics actually has to say about making it a reality. So let's start with the biggest question of all.
So let's just cut to the chase. Is time travel actually possible? Well, the answer is it's complicated. And to even begin to understand the physics, we kind of have to start with the fiction and even the ancient myths that got this whole ball rolling. Long before we had science fiction, this idea of time getting all weird and bendy was baked into our oldest stories. In ancient Hindu mythology, you have King Raivatakakudmi, who visits heaven for what feels like a day, but when he comes back to Earth, ages have gone by. There's a similar story from 8th century Japan, the legend of Urashima Taro. But it was really H.G. Wells, back in 1895, who completely captured our imagination with the time machine and put that idea in our heads that you could build a device to just hop through time whenever you wanted.
But that amazing idea immediately slams into this massive wall, a huge roadblock. Before we can even think about building a time machine, we have to solve this giant logic puzzle that's been stumping people for over a century. And this is the big one, the classic, the one everybody knows, the grandfather paradox. The idea is pretty simple. What if you go back in time and, well, kill your own grandfather before he meets your grandmother? If you pull it off, you prevent your own birth. But if you were never born, then how did you go back in time to do it in the first place? It's a perfect head-spinning contradiction. So how do you even begin to solve an unsolvable puzzle? Well, a couple of main ideas have popped up. The first one, over on the left, is this idea of a mutable timeline. So your actions literally split reality. You create a brand new, alternate universe where you were never born, but your own original timeline is totally fine. But the other idea on the right is a lot stricter. It's called the Novikov self-consistency principle, and it basically says the past is set in stone. The universe literally won't let you create a paradox. You can't kill your grandfather because the laws of physics themselves would stop you. Maybe you'd slip and fall at the last second. Your trip to the past was always a part of history.
Okay, so while philosophers were debating all these paradoxes, physics kind of blew open a completely different door. The answer might not be inside some mechanical box, but in actually bending the very fabric of the universe itself. And of course, this is where the main man himself, Albert Einstein, enters the picture. Back in '35, he and a colleague, Nathan Rosen, were messing with the equations of general relativity, and they stumbled onto something incredible. A theoretical bridge that could connect two super distant points in spacetime. We call it an Einstein-Rosen bridge today. The only catch? Their version was wildly unstable. It would collapse in on itself before anything could ever cross it.
The easiest way to wrap your head around this is the classic paper analogy. Imagine space-time is just a flat sheet of paper. Now, to get from one point to another, you got to travel all the way across the surface. A wormhole is like folding that paper in half and punching a hole straight through, creating an unbelievable shortcut. So, this is the crucial point. We don't just need any old wormhole. We need a traversable wormhole. We need one that's stable enough and stays open long enough for something, or, someone, to actually get through it without being instantly crushed into nothing. So by 1988, a couple of physicists, Michael Morris and Kip Thorne, they basically created a checklist, a recipe for a working, traversable wormhole. And most of it is just really, really mind-bending math, except for one ingredient. One ingredient that seems totally impossible. All right, so here's their checklist. First, it has to connect two flat, stable regions of space. Makes sense? Second, no event horizon. That point of no return you get with a black hole. Third, the tidal forces. That's the stretching and squeezing of gravity. They have to be gentle enough not to rip you to shreds. But this last one, this is the real kicker. The wormhole must be held open by something they call exotic matter. And that right there is the showstopper. Why? Because to prop open a tunnel in spacetime against its own insane, crushing gravity, you need a substance with a property that sounds like it's straight out of science fiction. Negative energy density. Okay, think of it this way. Normal stuff, like a planet or a star, acts like a bowling ball on a trampoline, right? It makes spacetime curve downwards. That's gravity. To hold a wormhole open, you need the exact opposite. You need something that's like an invisible hand pushing the trampoline up from underneath, propping that tunnel open against the incredible force of collapse. For decades, this exotic matter stuff just seemed impossible. But then, a little loophole appeared. thanks to the super weird world of quantum physics. A pretty recent theory suggests that the bizarre quantum effects happening around black holes might actually be the key. The model shows that charged particles zipping between two magnetically linked black holes could, maybe, generate the exact kind of negative energy you need to hold a wormhole open.
Now, this was a huge leap. I mean, it turned a theoretical impossibility into something that might actually be plausible. But could you really build one? And could a person actually survive the trip? Well, some recent papers suggest it might be more than just theory. So, is this our time machine? Well, not so fast. It seems like the universe has a kind of built-in safety feature. Stephen Hawking called it the chronology protection conjecture, which is basically a fancy way of saying the laws of physics will always step in to prevent time travel paradoxes. And these new wormhole models, they seem to obey that rule. They're shortcuts through space, not time. So that whole grandfather paradox thing we talked about, yeah, it's off the table.
And that brings us to the next massive step. A paper from just 2020 modeled a wormhole that could, in theory, be big enough and stable enough for a person to travel through without getting torn to pieces. But the scale of this thing, it's almost impossible to wrap your head around. The scale is just staggering. To keep those tidal forces from crushing you, the radius of the wormhole's opening, what scientists call its throat, would need to be more than 15 million meters. Let's try to put that number into perspective.
Okay, so a radius of 15 million meters means the diameter, the total width, is 30 million meters. Now, look at this comparison. Our entire planet Earth is less than 13 million meters across. The mouth of this theoretical wormhole would be more than twice the size of our whole world. And get this, that's just the opening. The length of the tunnel itself is even more mind-boggling. The minimum theoretical length for this shortcut through spacetime is over 3,000 light years. Which brings us to our final, absolutely mind-bending question. If the tunnel itself is thousands of light years long, how on earth is that still a shortcut? Well, the answer gets into the bizarre geometry of spacetime. The distance through the wormhole might be enormous, but the distance it lets you bypass in normal space could be billions of light years. It's a shortcut so vast, it completely redefines what far away even means.